Hey everyone, and welcome to another episode of Space Science with Python in our Near-Earth Objects project. Small recap from last time. What did we do? We computed the apparent magnitude, so the brightness of the objects in the night sky, by using the HG function that we introduced a few sessions ago, and compared the resulting distributions of all NEOs with the Pan-STARRS limiting magnitude, which is at around 24 Mach. And we found out that only 20% of all NEOs are currently visible for this particular survey, although of course the survey cannot look at all regions in the night sky at the same time. But where do these NEOs appear? Well, this is the question we would like to answer in today's video. So we will compute the sky coordinates of the NEOs with SPICE in our Python environment and plot them, and also do some filtering to see whether there are certain regions of interest for our observations or not. And this is a small summary what we are going to do in the next couple of minutes. So this is a small introduction, and as always there is the corresponding Jupyter Notebook in my repository on GitHub, so you can simply go here, scroll down to Project Near Earth Objects, and there you will find all corresponding Jupyter Notebooks, and the most recent one is the 08 Neo Sky. So I hope you will enjoy it, and if you would like to have a small deep dive, just stay here in this video, and in a few seconds we will start with the detailed analysis of each cell. Okay, we are back now here in our Jupyter Notebook, and I would say that we will directly start with the cell number 18 of today's session. And this is a small recap from video number 8 or session number 8, where we computed the position of objects in sky coordinates using matplotlib. So this is a small cell here where we use the so-called ITOF projection and then compute the longitude and latitude values. And then we have to do some, let's say, magic layout formatting to draw the degree values. And then we can simply have here a nice sky map of in ecliptic coordinates. So this is what we are going to do today. We have here the longitude and latitude, and we would like to draw all NEOs of today's date, and also maybe some corresponding or some other objects in the sky. So what can we do to orientate a little bit in this plot? Well, the most obvious things, or my suggestion would be to draw or to compute the position of the sun. So in cell number 19, we are going to compute the position of the sun as seen from Earth. So here you see the Earth to sun vector. We use the sun to Earth vector and just invert it. And then we use the SPICE function regrad here, where we just put the position vector as an input, and as an output we get the distance between the sun and the Earth, which is now here not being used. We get the ecliptic longitude and ecliptic latitude as additional output values. And to an additional orientation, I would also like to draw in the opposition of the sun. So where the opposition effect of the brightness curve appears, and this is 180 degrees away from the longitude. So I just simply add pi to the longitude, and then also I apply modulo on 360 degrees to really not exceed or go over 360 degrees. And the latitude value has to be inverted as well. But in this case, it's, I think, almost 0 degrees, so it doesn't really matter. Additionally, as in the video, we need, video number 8, we need to do some, let's say, magic maths to compute the longitude values for matplotlib, because matplotlib does not work from 0 to 360 degrees, but more from minus 180 degrees to plus 180 degrees. This is also why we did this small magic thing here in cell number 18, where we just replaced the ticks. And this is being now considered here. So I compute here the ecliptic longitude for plotting, so to speak. And additionally, we can also plot or print the longitude and latitude values of the sun. And for today's date, so the 9th of October 2022, the sun is at around 195 degrees longitude in ecliptic coordinates. And we can simply use Stellarium to verify this. So here's the sun. That's the current date time. So making this video now at around 6 p.m. in the evening. the sun is setting, and we see here that it's around 196 degrees. So I think, yeah, I executed the Jupyter notebooks a few minutes ago. So not even a few minutes ago, I think even yesterday or so. So this is this should, yeah, this is almost correct, so to speak. So we can say, yeah, this works. I didn't mean to zoom into the sun. So let's go back here, and we can go to cell number 20, where we simply plot the sky map again, and additionally we add the sun, and we add the what I call now the opposition point. So let's have a look. I didn't add a label or a legend or something. We have simply here the sun on the right side at around 190 degrees, and here the small teal colored rectangular shape thingy is our opposition point, so 180 degrees away from the sun. We are going now to cell number 21, and here in cell number 21 we use the apply function on our data frame. So here you see in almost every call, and what we do is we use the vector from the the NEO to Earth vector we computed last time, and just invert it now to the vector Earth to NEO, and then we compute the distance, ecliptic longitude and latitude for the NEOs as seen from the Earth, and then also additionally a column where we have the longitude values for matplotlib. So let's execute this cell number 21, and here in cell number 22 we have our final cell where we are plotting these NEOs. But yeah, here it is. We are plotting them here with a small marker with simply dots and in a light sky blue color. And we do some filtering, yeah? So you can now play around a little bit. You can adjust the apparent magnitude, the absolute magnitude, even the distance and so on, to see what kind of effects we have. So here in this example, we are only taking a look at very faint objects, fainter than 25 Mach. Also rather small objects, larger than 22 Mach, and objects that are quite close to Earth, so smaller than 1 AU. And if we plot this, you see here the result. So here is the sun, you have here the opposition point, and yeah, of course, I would say, yeah, let's say 50 degrees around the sun is like a dead area, because during the day we can't see or observe anything close by. And then if the sun sets at some point, then we have to wait for a few hours so that the sky is dark enough to conduct some observations. And then we can start detecting, observing NEOs. So in the future, we will also get rid of all these objects. So let's say, yeah, we may maybe draw a circle of 50 or 45 degrees, where this is like a dead area. We can't observe anything. And we see here that we have like two areas of interest. Yeah, they are like not at the close to the opposition, but somewhere between opposition and the sun, where we have some objects in this particular case. And it could make sense, because if you try to imagine the sun in the center and the Earth at 1 AU, and then draw also the opposition direction, and then check the volume you are observing of the solar system, let's say in a radius of 1 AU, you can draw the NEOs and maybe compute also the corresponding values like phase angle, distances, and so on, and also dwell time, be depending on the orbital elements. You get a very multidimensional problem, and in this case, the optimal, or the most objects in this case, they are gathering at around, I don't know, 60 degrees, 60, 90 degrees away from the opposition effect. So this is somewhere where you should then, opposition direction, where you should conduct your observations. So you can say, hey, does the opposition effect does make any sense, or does it have an effect? And yeah, we can of course change our filtering a little bit. We can say, okay, we are interested in values or apparent magnitudes that are smaller or equal the limit of the Pan-STARRS observatory, and maybe observe maybe larger objects, and maybe also only within a radius of a quarter AU, so only objects that are very faint within the limiting magnitude range, that are also rather small and that are close by. So let's have a look how this looks like. And there you see it's a little bit more scattered, but there is no certain region of interest, like at 60 degrees. It scatters around, let's say, the opposition area, right? So we have here like around 60 degrees around the opposition direction. We see most objects, and far away it's getting fainter and fainter, or not fainter, but you see less objects, so it doesn't really make sense to observe them somewhere else here. And we can, of course, change the observation, like we would like to see everything until 5 AU, and then you see really these two regions on the left and right hand side, they are not present at all. Everything gathers around the opposition direction. So you get a small gist that this is a really multi-dimensional problem. It's not that easy to say, hey, you have to look into this direction to observe these kind of objects and so on. We are not also considering any orbital elements, so maybe there are certain regions of interest for certain objects or objects with orbital elements. Also, the regions you saw here on the left and right hand side, maybe this is an selection or observation bias, right? Because maybe with our current strategy on Earth, we observe objects with a preferred and within the preferred range of orbital elements, for example. I mean, who knows? And this leads then to blobs on the left and right hand side from the opposition direction. So you see, this is a very multidimensional problem and not easy to answer. In our next video, and I will upload the next video next week already, we create a small IPython widget where we have some interactive tools where we can click around and see, adjust the values a little bit more dynamically than here. Yeah, so we can maybe, I don't know, these values like 25 meg or 26, we can adjust them more easily. And then we will get maybe a better feeling and understanding how this looks like. The next step, I mean, we would like to determine some kind of observation strategy. We will continue working with the apparent magnitude. So in the next videos, we will then compute, for example, the time. How long do we need to continue our observations until we detected every NEO? Yeah, assuming that we see the entire night sky completely, like we take a picture of the entire night of the entire sky all the time. This is of course not realistic. Yeah, we see only a part of it, and then only during the night and so on. And then in the later video, we will also continue working with a more realistic approach. We will use the camera properties, the telescope properties, and so on. So we add even more complexity into this kind of computations, where you can later adjust the exposure time, the quantum efficiency of the CCD, and what's or not. So every property of the CCD and also of the telescope, the diameter, the reflectance of the mirrors, and so on. And then we will also use not the already known NEOs, because maybe there is a certain bias, but we will use a simulation model. So a model that has been created, I think, 1.5 years ago, the most recent model. And we will use the model to see, okay, does the model deviate from our actual known NEO distributions, and how do we need to adjust our observation strategy accordingly to find all potential risks for our home planet. Yeah, I hope you learned something today, and I hope you still like coding. It's getting autumn now, so you have maybe some more time in the evening to do some learning and coding, and I hope that this video series is a part of it and that you still enjoy it. If you have any questions, just reach out to me here on YouTube, reach out on Twitter or Reddit. And yeah, you see, with small steps, we continue our scientific journey, and I hope you enjoy it, and I hope to talk to you next time. Cheers.